Hello everyone, I am Xiao Gang. Okay, we are going to learn something simple and easy. We are learning this removal. This is relatively simpler. First, let's look at the documentation. Here, UMO is used for removing elements from numbers. Remember, UMO requires this partition operator. It needs the equality operator to perform a removal. So, I'll remember it removes everything. Actually, this is a bit like when we took math exams before, and you look at this sentence, it has many keywords. The front part defines the removal of elements. Right, first, you need to overload this equality operator. All elements of equal value. So in this place, it declares an array, and this is the initialized array. So it removes 20. Then there are two 0Cs inside. Then both of these 20 will be removed. And then at this point, list where with or wait. It should be for convenience. It copies this array here once. It might still need to use this array later on. And then this RemoveSingle erases the first matching element. So we only want to erase it this way when using just one. Then this RemoveAnd. Note that you need to distinguish. You can add single, which erases the first one. It is equivalent to it only erasing the first 30. Then here you can find that there is a 30 here. The 30 after this one was not erased. Then this RemoveAt performs a removal according to this index. But sometimes we might need to determine whether this index is valid. So if the transfer is invalid, it will be out of bounds. And this will cause a runtime issue, meaning it will throw an error when you run it, because it doesn't actually have this many elements, right? So let's write a simple example here. Okay, let's just attach it here. It should be okay. Okay, when we get to this part, let's write it below. We call it xg remove element. And here we still have both comparable. And this one is relatively simple. We just validate several at once. Okay, let's take a look at this. This is our original data array. And this place has changed its name. This is also normal. To change the name, we just add UE. So essentially, you can look at this red. It is actually very simple. Just the number of elements in an array. It's equivalent to this kind. Returns an element from the set. And here you're passing a set, right? Right? And then here it removes another one. We won't go any deeper with this. So basically, you can understand that this is red, right? We should actually take a look at this. Actually, you can write it like this. Just write it like this. Actually, there's no problem with that. Actually, writing it this way might not look good. Number. Right? This way is also fine. No problem. So let's use this one. It's actually the same. I will try to demonstrate it more for everyone. Then this spot is equivalent to removing a 20. Okay, no problem. So if we do this here, it removes the first one. This removes a 20. Remove the first 30. So it is remove. This is the expected execution result. So we move out the second shadow from this place, where finally we make it quest OK. So let's run it now. Let's hit a proper point. Please like, subscribe, share, and support Mingjing and Diandian. Oh, right, okay. Actually, what we want to do is this. It's Cyric. We want to call this function. So look at this max. It will be scaled down because before it was 9. Now it has become this 5. So I want to demonstrate this to you. Okay, I'll take a look at this. I don't know if they mention it later. We should mainly focus on this. This is the memory used by this data array. And make it as small as possible, and then minimize it. And then save this type of element that has been saved. I mainly want to demonstrate this to you. Okay? Then let's continue to look at the next part. So here, we actually remove all. If we want to pass such a large format, then we can use location for determination. So this side will make a determination. That is, if it is divisible by 3 for all. Then it will perform a modulo operation like this. Let's take a look at the remaining ones. Actually, there are other paths here. Swipe, because in this area, after you remove an element, the following one will move to fill the gap. It's equivalent to having a stack of cards, and you remove a few cards from the middle. The cards behind will sequentially move forward to fill the gaps. So this actually involves certain overhead. However, it maintains the original order. If we don't care about the numbers in this, the order of these existing elements, then we can call RevSwipe or RemoveSwap or RemoveSwap to reduce this overhead. So it's mainly that we can't guarantee this order. Look at this spot. We add 12 value 124 to 15 value 123 for T, 5 here. We remove swipe 2 here. So it should be like this. Removing all elements that are 2, and then you'll find that the entire sequence has been disrupted. Then this places, remove the element at the location where the shadow is 1. You need to note that this place has some ants, or places that do not have ants. So the element where the shadow is 1 currently is 1. After removing it, this element is removed, but the order of other elements will be disrupted. And this is equivalent to, it is the same as this. It's just that their original order will undergo a change. So similarly, here, to do a simple implementation like this, we give it a function like this, that is mute. We will try to implement it. Let's set a speed like this. We will still give it. Okay, let's take a look at the results of the run. We give 3 hosts. Or let's run the simplest one first. That is, we make it erase. Erase it in this way based on the input position. So, it. Then everything that can be divided by 3 will be removed. Then obviously, these 2 30s will be removed. There is absolutely no problem. Okay, so we'll adjust this part. If we change it to 30, no problem. We will try to execute it here. Let's run them all together. We'll just have to delete this one. Then we can take a look at the next one. Here, there is n, which means remove all of these elements. We will explain this to everyone together. Actually, sometimes we like to omit this. We drop the clear, but it seems like it's not there, right? We just use n and we'll mention it. Actually, there's also a push here. Oh no, we haven't explained it to everyone. But actually, if you click into it, you will find that it's actually the same. It's just the dropped add. So, what does this push mean? It's actually a concept designed to maintain compatibility. So, it's like this. Okay, let's just add an empty one like this. The order here might not look good. Then let's make it a bit more organized. Let's write it manually. 1、2、3 考1、2、3 4、5. Okay. Then at this location, we will remove all available layers, components, after we finish removing them. We will also try to rework this data. Then we will set all of it equal to 2. you can see this notice. We shouldn't use this method. We can take a look. Here, we remove all instances based on the given object. This version is very effective because it doesn't guarantee this order. So it is very effective. Similarly, let's bring this up again. Look, this removes the element at a specified index. We remove the element at a specified index, grouping them together like this. Let's remove the 0th one, removing the element at index 0. And finally, it's the method for this position. Let's readjust it this way. Note that there's a swap here. There shouldn't be any problems here. Okay, next, remove all 3. Next, let's execute this. Let's take a look at the removal operation. What is the result of executing it this way? Okay, we have successfully opened it now. After opening, we call a remove like this. XD should have XD mu. Various ways to remove it. Let's check if there are any breakpoints. There should be a breakpoint after the check. No problem. We can start it directly from our side. We have already processed these numbers for the first time. There are 9 elements. They are as follows. Then, after removing all the 3 after they are removed, look at its 124. 80,100 T-port is completely fine. We will reinitialize it once, and then it turns into this way. Then we remove all that are equal to 2. Did you notice? We really don't have 2. But how did this 5 move to the front, right? This 143, its order is messed up again. No problem. So let's go this way and remove the first element. We will reinitialize. Now, initialization is complete now. We only removed the leading one. You'll notice that after it's removed, the internal order is indeed scrambled. No problem. So we will reinitialize this side. We will also remove what is related to 3. And then you will notice that this 3 is indeed gone. But this 5 is in front of 4. This is clearly incorrect. Isn't this 5 supposed to be the last element? So that concludes our explanation of the removal operation. Yes, what's worth noting in this area is that in this spot, let's activate it again. Then you will find that every time it is emptied, right? It's gone after emptying. Look, empty. We add it again. It actually doesn't exist after emptying. You will find that array number and array max are gone. It's equivalent to this empty. We look at its comments. Completely clear this array. And then it will call the construction function of this structure. If there is one, it basically means something like this. In fact, you can pass a class. That is to say, slack is optional. And then we hope that after this construction, what size will it maintain? That's roughly what I mean. So we hope that after it completes the absorption, it maintains a size of 10. Let's see if it can maintain this size of 10. Okay, after we finish executing, we'll skip straight to the final step, okay? Look, you can see that its max is exactly 10, but it doesn't have any elements inside yet, right? It's just like this situation. So actually there's a concept here. That is, if you involve many hosts, you'd better make it fixed length. You know your inventory is 30 slots, then you won't need this negative feedback loop. You can directly solidify it into 30, right? Then it is fixed at a size of 30. For example, you always know your backpack only has 30, but if you do it using automatic expansion, it will make it 40 items. So you essentially have the space for 10 backpack structures. You're wasting it. This is a very small optimization, but if we accumulate them little by little, it will actually cause a relatively noticeable impact on the entire system. Okay, so regarding this removal operation, I will now conclude the explanation. Thank you all.